Please.
Okay, so first, let me say thanks very much for the opportunity to come here and tell you a little bit about what I and my research group have been working on and my collaborators. So as the title suggests, I'm going to try to be talking about 3 different themes, and I'll try to bring them together and explain what they have to do with one another. Alex told me I should try to make this somewhere between colloquium and special, so I probably have not succeeded. But kind of put it at a, just to kind of start very slowly, I will move faster. Here are some numbers. Oops, let me get rid of this. How do I get rid of that? Get rid of you. Okay, here are some numbers. There won't be very many numbers in this talk except for 1, 2 pi, and i's and things like this. But just to kind of set the stage for some numbers. Let's see. Okay, here they are. H bar, like constant.
Those are all fun.
They will be in just a moment. They will be in just a moment. Yes. So I'm going to step through each of these, what they're about, and then how they how they're going to inform what I'm going to talk about today. Okay, so quantum theory, of course, I just picked some of my favorite pictures involving this. There's, of course, many, many more. Everybody in the room surely knows many things. I just picked hydrogen atom photoelectric effect and some rendering of a quantum computer. Relativity, this idea that there's a absolute speed barrier that we have, speed of light. And here we're just drawing a picture of a light cone. And then, on the other hand, gravity. So the same physics which is governing planetary orbits, black holes, apples falling off of trees. All that stuff is kind of controlled by Newton's constant. I've written it here in these units. And then, as Keith already mentioned, why are you bothering with that? Well, you should set most of these to 1. And indeed, that's where we're going to be living. We're going to be living in a...
Do the other one at 1, too.
I will. I'll turn that one into... Well, it is an energy...
Square root of 8 pi.
Yeah. So I'm going to be working in units where quantum mechanics is going to be very prominent. Special relativity is going to be very prominent. So we're going to be talking about a quantum system, a relativistic system. And at the same time, when you work in these units, there's essentially everything in terms of powers of energy scales, either inverse or positive powers of energy scale. So I'll have Newton's constant being represented like so. And even more conveniently, there's going to be a particular energy scale, the Planck scale. I'll just represent it like this. You might want to throw in 8 pi's. But the point is that it's a very, very big scale, big energy scale relative to kind of places where we have experimentally probed things more directly. So to just give a reference, electron mass is down at, say, 5 MeV. Planck scale is much, much higher. Okay. So what is this talk going to be about? I'm going to try to gather 3 themes where these units and these energy scales, these processes are all playing some kind of role. So on one hand, I'm going to be talking about quantum field theory. Now, we of course use quantum field theory all the time to describe many short distance and interesting phenomena. But from the point of view of, say, the Planck length or the Planck scale, these are actually long distance phenomena. So things that can emerge at longer distances relative to what is going on at a short distance scale. So that's going to be one piece of what I'll tell you about today. On the other hand, I also want to talk about things connected with the shorter distance scale, so things associated more directly with quantum gravity. And by that, I mean places where Planck scale physics can play a more prominent role. And we'll be going both from asking how do things go from short distances, maybe I'll stop using this point there, going from short distances, at very high energies down longer distances, so these kind of low energy emergent phenomena that we might have in a quantum field theory. And on the other hand, lessons we might draw, constraints we might understand from working at long distances and then asking, does this inform what is going on or constrain what can happen at these shorter distance scales? So you might want to speculate endlessly about how you can go from here to here, but trying to put these together is not always a trivial task. It's very, very difficult. And the kind of uniting theme that's going to bring these together is symmetries. And okay, I tried to make this a circle, but symmetries is too long a word, so it's not as symmetric as it should be. But so goes. So the point is that we're going to try to be bringing together these 3 themes. And I'll try to explain what each of these is as far as I'm going to be talking about it today and what they have to do with one another.
Use distances, but you put energies and units. So in terms of energies, this what?
So this will be a very, very high energy.
And this one?
This is a very, very low energy. So this is, say, 10 to the 19 GeV, something like this. And this will be, low energy for me will even be something like 13 TeV or something like that, which is, of course, very, very high energy, of course. But from the point of view of the even bigger energy scale, it's low. That's right. Okay, so what's quantum gravity? So for my purposes today, it's going to be where we're working in these, of course, units, and going to have Planck scale very important or featuring prominently in some way, either directly or indirectly, everything I'm going to say. And depending on who you ask, you will get different answers about what it is. So I think the honest answer now is that it's a work in progress. There's pieces of it that people would claim to understand, but kind of putting it all together in terms of a coherent framework is, I would say, very clearly a work in progress. Now, for what I'm going to tell you today, there's some specific ingredients that I'm going to use. And this is what I'm going to mean by quantum gravity today, using things from string theory and related subjects that kind of had their origins in string theory, but now have kind of departed in some ways. One is going to be this idea of having like a closed loop, so not a point particle, but something that has some finite extent. And then the fluctuations of that are going to be things like a quantum of gravity, the graviton, if you like. We'll also have open strings, things that end, and then the endpoints of those strings, so-called dynamical fluctuating branes. And then a famous or infamous fact, depending on who you ask about string theory, is that it has extra dimensions. There's different ways of describing the same kind of phenomenon in string theory. So there can be similar to how you have high and low temperature duality, like say an Ising model or something like this. There's generalizations of that, which are pretty remarkable in the context of string that are going to play a role. And then lastly, holography, a very interesting idea that a purely non-gravitational system can nevertheless still characterize a gravitational system in higher space-time dimension. So there are some ingredients that we'll be featuring later on. Plus many more. I mean, this is not meant to be an exhaustive list. There's many other things that I can't talk about. You probably have your own favorite list, but there's many more things to say here. Okay, now how about quantum field theory? Now again, depending on who you ask, you will probably get different answers about exactly what it's supposed to mean, but it's going to be quantum mechanical, so I'll set this to 1, and it's going to be many degrees of freedom for me that are interacting locally in some way. Now, it's often very inconvenient to specialize to relativistic systems, but strictly speaking, quantum field theory can be applied in very, very broad settings. So surely I can give you a definition of this. This is also a work in progress, I would say. It's remarkable that it's a very, very useful framework for describing many phenomena in nature, but it's also true that people are discovering these techniques to calculate in known quantum field theories. And there's even quantum field theories that are being discovered that you may not have known about. They're being discovered and analyzed from that point of view. And I'll touch on some of that as we go. Okay, so here's just a few of my favorite examples. I'll step through some of these. I'm sure you have your own, ranging from particle physics, cosmology, fractional quantum Hall, to pure mathematics. All of these kind of show up. There's many more applications. I don't want to say that this is like the list. This is just one I happen to like. So plus many more. Okay, so what is symmetry? This is going to be the other thing that I'm going to talk about. So again, this is a kind of very celebrated concept in physics, math, and more broadly, where one uses, say, constraints from conservation rules and selection rules to constrain the dynamics or processes that take place in some kind of system. Okay, so what is this? Remarkably enough, this is also a work in progress. The notion of what a symmetry is has kind of been growing and undergoing kind of various levels of abstraction and generalization that are continuing to this day. And I'll also be touching on all of that. Okay, so, which probably sounds surprising. I mean, Noether's theorem, of course, is very well established, known for over a century. What new could there be? Well, it turns out that there can be many new things happening. Okay, so here are some examples that I happen to like. So, time translation invariance, converting kinetic energy into potential energy. Perhaps simple, this would be conservation of baryon number. And then more abstract notions that I'll touch on as we go, involving so-called generalized symmetries. I probably will not be able to talk about this one. This is something just I grabbed from my recent paper I wrote involving quantum circuits. But anyway, there's many, many different kind of generalizations of symmetry that one can, in principle, talk about. Okay, so I told you that all of these things were works in progress. So what will I talk about? Well, so the idea is going to be to use symmetries to inform our study of both quantum gravity and field theory, and conversely, how to use things we think we understand about gravity and field theory to broaden what we mean by symmetries. And one of the things that's going to happen throughout, as I'll get to it, is hopefully I'll get to it, is this remarkable correspondence between certain topological structures showing up in field theory, to some extent in gravity, and certain symmetry structures. Okay, so I told you I want to talk about symmetries, field theory, and gravity. A puzzle to keep in mind is that, and I'll come back to it a few times, is that there's certain notions of symmetry and conservation rules which are totally fine in the context of quantum field theory without gravity, but apparently once you start switching on gravity, including things like quantum mechanical black holes, something seems to go wrong. So you throw some conserved charges into a black hole, and you ask, what happened to my what happened to my wonderful conservation? Did it get lost forever inside the black hole? Does it somehow subtly escape? This is a motivating puzzle. And I'll come back to this puzzle a few times, but the main question is, what happens to interesting particular global symmetries in quantum field theory once you start switching on the effects of gravity? Okay. So here are the three topics that I'll be talking about in various ways. Let me now talk a little bit more about field theory. Okay. So I'm still doing, if you like, review. Okay, so it's a useful subject, I'd say. I just grabbed this from Atlas at some point. Whenever you're calculating particle physics collision processes, you're of course just using quantum field theory in some way to calculate both, what's happening with the incoming states and then the kind of products that are going to be produced. And of course, a very famous quantum field theory that's used all the time is the standard model of particle physics to kind of predict and see whether there's any deviations from the predictions of that quantum field theory. Cosmology. This shows up in many ways. So for example, inflation, what's causing the kind of a rapid expansion of the universe early on, small perturbations, what you see in later times, controlled by quantum field theory. Classic examples like when things start decoupling from a thermal bath, also controlled by quantum field theory calculations. Okay, and here's an example from condensed matter I happen to like. If you look at fractional resistivities, you can think about this fractional quantum Hall effect in terms of a particularly, many aspects that can be captured in terms of a very simple 2+1 dimensional quantum field theory, type theory. It's remarkable that it can capture so much. It doesn't capture everything, but it captures a remarkable amount. That same quantum field theory shows up, remarkably enough, in pure math, just in terms of classifying different kinds of objects in knots and topology. Same kind of underlying field theory, but a totally different set of seemingly different applications. And then, okay, here's more, 4 manifolds. This is a picture of an engine. That's a different kind of manifold, but okay, and many more. Okay, so this is not meant to be representative again. It's just some examples I happen to like. So you probably have your own favorite ones, but yeah. So how does it work? Now so there's a textbook approach, and I put textbook in quotes because I think at this point even the textbooks recognize, or the new ones recognize that sometimes this is a bit limited, but there is kind of a conventional way to kind of go about, at least start getting into calculations pretty quickly, involving a path integral where you start here, you finish here, you just sum over all the possible trajectories, and then there's a sense in which you weight them by complex phases by a so-called Lagrangian or some quantum mechanical generalization of what you'd want to call the Lagrangian. Okay, and you can calculate many interesting things when you do this. So for example, electron-positron annihilation into another pair exchanged through a photon, or something that will probably be interesting to look at in terms of Higgs physics later on is in terms of gluons fusing, like say 2 protons banging into each other, and then producing say 2 Higgses at the end. All of this is governed by kind of the rules that you can kind of extract directly from like path integral formalism. But life isn't always so simple. So sometimes, even if you have the Lagrangian, it's hard to calculate with it because there may not be like a small expansion parameter to compute with respect to. Even defining some of these field theories can be rather subtle. So I'll give a couple examples later where even trying to figure out that you had a quantum field theory in the first place, you can kind of extract that there's some kind of local interactions governed by fields of some kind, but even defining what you would mean by, say, the Lagrangian or the operator correlation functions becomes much harder to pin down. So these go under the name of non-Lagrangian. I'm not sure it's the best name ever, but this is how they're defined. They're spoken of where it's you kind of know that the field theory exists, but it's very hard to kind of pin down many of the properties of the field theory. Surprisingly enough, you can even use string theory and quantum gravity, taking different decoupling limits where Newton's constant is sent to 0, Planck sent off to infinity, to find new examples of these field theories. Okay. So there's many complicated examples, and what we're going to do is see that we can use symmetries to hopefully help us understand some properties of these, just to understand selection rules and so on. Okay, so that's field theory. What about symmetries? I just mentioned that I'm going to try to use symmetries. So what is a symmetry here? Okay, so what's the kind of conventional definition? We imagine we have some unitary operator. It commutes with some Hamiltonian. And I'm going to talk about two different kinds of symmetry, if you like. One is kind of a true symmetry, which kind of takes me from one state to another. They're not equal. And then there will be another one where I should really be thinking in terms of a redundancy. So it's not technically a different state in the physical system. It's more what we call a gauge symmetry. But both are going to play some role. And the ones that have been kind of seeing some kind of strange modern incarnations where things have been generalized in various ways are really these global symmetries. And these redundancies and also have to be generalized in some way as well. Okay, so a surprising development, or at least an interesting development from about 12 years now is that global symmetries have surprising topological characteristics that you may not have thought about. And basically the idea is to think about Gauss's law surface that's capturing some flux lines or some generalization of that. And then the shape of the Gauss's, the encompassing surface that's capturing those flux lines. The shape doesn't matter too much. You can kind of deform it in some way. Doesn't matter. So this kind of picture can be used and say some interesting things about kind of how symmetries act upon kind of operators in your quantum field theory. So here's an example where you have some local operator here, and then some surrounding kind of Gauss surface, something like this. And this is in d dimensions, so this is including time. So d minus 1 space, 1 time. And we have some local operator just sitting at a point in the space-time. And then topologically, it links with this thing here. So in other words, if I try to pull this thing through, it's always going to bang into this dashed surface here. But the important point is that as long as I'm collecting all the flux lines that are emanating out from here, it doesn't really matter what the shape of this is. I can deform it in any way. So in this sense, it's a kind of a topological thing. Topology is being this branch of math where local deformations do not really affect what I'm doing. So if I shrink it down, then it's basically the action of the symmetry on the operator we're talking about.
I have a very naive question. Why did it take until 12 years ago to come up with this idea?
Oh, this part here?
Yeah.
Oh, this part here is fine, and people knew about variations of this part, I think, for what we're calling zero-form symmetries. But what we're going to do is start abstracting away from this particular example. So this is just kind of like the warm-up. So
what's in that paper is well beyond what you just said.
That's right. I'm going to tell you about so this is kind of like the warm-up, and then it's kind of it mutated into its own kind of entity, which is kind of vastly generalizing away from just this. So this one, of course, everybody knows. Maybe I can write on the board. So let's just say we had like a conserved current or something like this. We could just, oops, it's okay to write on this, right? Okay, I'm on the whiteboard.
Yeah.
I might have, say, the time component here for my conserved charge, and then just integrate it over some three-dimensional manifold, like that. Better. And there's some number front. Sorry. So I have some number of tests. Say, okay, I have some charged operator, and I just have this guy acting. That's, of course, a very well-known story. Not meaning to, say like, amazing. They figured this out. But what they did do is they started asking about, other kinds of operators. So one of the kind of recent insights is that when you try to define what you mean by the field theory in the first place, there could be not just the local operators, but also extended objects that are also playing a prominent role. What are the global symmetries of those things? This is where it gets a bit more interesting. So here I've drawn, for example, a line. This is the red thing, which is going to be acted on. This is the thing that's carrying the charge. And it's being acted on, again, by a symmetry operator. Now, topological linking tells me I don't want to talk about a d-1 dimensional object anymore. It's going to lower the dash thing will lower its dimension, and then it acts in some way. And again, this part was kind of pieced together and known about. I don't want to claim that these guys were the first to do it, but they had this kind of uniform way of thinking about it, which I think has been very fruitful. So this would be called a one-form symmetry. One here just refers to the fact that this thing is carrying one dimension. Yeah, that's it. And then once you have this, you can start generalizing to things that are supported on, say, surfaces or walls or however many objects you want to talk about. And the other kind of really remarkable thing is that this dash thing, even though you want to think about it as just kind of some Gauss's law type surface, it itself carries an interesting quantum field theory. It's a particular kind of quantum field theory, one that doesn't depend on distances or scales in any way. It's a topological field theory. You can think about it as, if you want to think about it in terms of an actual system with excitations, you're kind of always living below the excitation, below the gap, the energy gap for making a particle fluctuation. So for my purposes, it'd just be what we would call a topological field theory. And those topological field theories, for example, were featuring when I was talking about fractional resistivities and manifold, not invariance. It's these kinds of things. So this object by itself starts coming to life in its own right. And that's one of the remarkable developments that then, if you start multiplying things together, you don't always get a group law like you had from the classic Wigner type statements. You start to get more general types of multiplication rules. So you take two of these guys together, and it doesn't always just spit out a third one. It starts spitting out summations over all of these different ones. So these are sometimes called fusion rules. So for example, when you take u dagger u, it doesn't necessarily just equal identity. It can equal identity plus other pieces. And these are all, there's kind of a non-trivial thing living on the symmetry operator itself. So these dash blue things, the symmetry operators, again, are these dash guys here, and they're acting upon different kinds of extended operators or defects in our quantum field theory. Okay, so this has had many applications over the past few years. It's led to kind of new order parameters, if you like, different ways of talking about symmetry breakings in different kinds of systems. In pure particle physics terms, it's led to kind of interesting new proposals for kind of flavor physics, new selection rules. I know some of the papers from folks here have been exploring aspects of that. And also something I'll be focusing a bit more on as we go is what it has to do with quantum gravity, in particular new objects and structures. So remember I had this puzzle. I just told you, well, somehow the notion of symmetry itself has started to mutate and evolve in the past few years. And I told you that in thought experiments, there's something puzzling about what happens to conservation rules in the context of gravity. So the global symmetries, these are all global symmetries. They are not gauge symmetries that I just told you about. They're very helpful in quantum field theory and selection rules. But there's this general lore, which has been explored both in the context of black hole physics, also configurations with wormholes and things and related backgrounds, that one should not expect to have global symmetries in quantum gravity. They're either kind of by some effect we don't have, and the effective field theory controlled by the quantum field theory, or they're gauged in some way. So what happened to all the global symmetries from this point of view? There's all these beautiful new mathematical structures. Where did they all go? Or do they stick around? Is this an exception to the rule? And secretly, they are still there in gravity, and we just clever enough to spot these more general global symmetries. So what happens to these global symmetries? And that's what I'm going to spend, I'm going to motivate most of the rest of my talk to focus on. And the slogan here is that they're either broken or gauged. So what do we mean by that? Well, so one way to get rid of it from kind of, if you didn't know anything about what's clumping in at short distances, there is a way to kind of destroy this topological linking I was telling you about. You could say, I gave you some quantum field theory, but I forgot to tell you about all the states of the theory. There was secretly a state, it was only excited at some higher energy scale. If I included it, then the topological linking we were talking about would no longer hold. So before we had this, so I can illustrate this with my fingers, I think. So I had some topological linking like this. I can't pull my fingers apart. Now it's impossible in 3 spatial dimensions, but if I loop it like this, and of course I have the tip of my finger, I can shrink it off and nothing happens. So there's no symmetry action anymore. So in other words, the symmetry operator doesn't really act meaningfully anymore on these kinds of heavy defects with states attached. Okay, so suppose I just start adding in new states. Then I can surely destroy or get rid of all of the global symmetries I had. And if I imagine that there are very high energies, I didn't have enough experimental power to get up to that high energy scale. This would be one way for me to have these things disappear. Conversely, I could say, well,
may I ask a question?
Yes, please.
Is this a very nice but maybe very abstract. Could you give an example in some real world situation? What kind of object this line is? Let's like cosmic string or what is psi nu?
Yeah, sure.
What heavier systems you keep in mind? Something more tangible.
Okay, yeah, so let's take Maxwell theory. There's no. Maybe I'll write it over here. Okay, so for my purposes, it will be U1 gauge theory. Yes. So the line operator that I'm going to talk about is just going to be an integral over the line of, say, the gauge field.
Okay. A closed line or?
No, we'll have it go from, say, minus infinity to plus
Okay.
infinity in time, something like this.
Okay.
You can make it a closed line too. It won't. Of course, there's boundary conditions you have to worry about. But okay, so this will be the operator. So this will be playing the role of what I was calling O of L. And then what will be the role of this dashed guy, right? So this dashed guy is going to be played by this guy here. Sorry, there's also a magnetic guy I could talk about. And then the point is that there's a canonical commutation relation between this guy and this guy, which means that if I try to pull it through, I pick up a phase. Okay, so there will be this other guy here. Let's do with this. So this is the kind of starting point where I see.
Okay, what is this circle which you draw?
That'll be this. It's really a surface.
Huh?
It's a linking surface.
Just Gauss's surface.
Ah, Gauss surface.
Yeah.
Okay.
It's the Wilson line is a Gauss's.
Okay.
Yeah.
Okay.
Yeah. And then if let's say I pull this thing through, the commutation relation between this and this is going to produce a non-trivial answer.
Which one?
You measure the charge of the Wilson line.
Yeah.
Huh?
This is just measuring the charge of a Wilson.
Yeah.
Yeah.
So that's the answer. You get a phase. You put IQ times.
But what's in non-trivial?
Not one.
Okay.
Yeah, so the point is that this thing is going to rotate by a phase, like we just said. So some phase.
Okay.
Okay, so that's the story for just Maxwell theory. Now what I'm going to do is I'm going to say, well, no, I forgot to tell you about electrons in the theory, okay? But let's make it a little more interesting. So let's not just do straight QED. Let's imagine that the electrons didn't have charge plus or minus one, minus one. Let's imagine they had charge Q. Okay, so let's now add in some guy like this, and I'll have some charge Q.
Mm-hmm.
Okay, so now we can talk about pair creation of these guys. So we can have our thing, and then, okay, let's also give it some big mass. We can have pair creation, and so we can snap the original line that we had, like this, and then the original topological linking that we had is going to be destroyed. Now, what will be left over from this process? I don't kill the, so this would lead us to what we would call a U1 electric one-form symmetry. One form because it's a one-dimensional thing like this.
Mm-hmm.
Now, if I add in these charge Q states, then what's happening is I haven't completely destroyed all of this. It's partially screened. And it's partially screened down to a Z mod Q.
Mm-hmm.
Now, in the case of like honest QED, where I have charge 1, it's completely gone. And you can do the same thing with the magnetic fields and the magnetic gauge field instead, where you could. So this Maxwell theory turns out to have a U1 electric as well as a U1 magnetic one-form symmetry, where you swap the roles under electromagnetic duality of the gauge fields. And from this point of view, you can start breaking it. So that's a helpful example to have in mind. So thanks for. And then, okay, so there's many generalizations. So, for example, you can do this in Yang-Mills theory with different kinds of matter fields and different kinds of representations and get different answers for what the higher form symmetries are going to be and whether they're surviving or not. Yeah. Does that answer your question? Or?
Yes.
Okay, great. Okay, yeah. So you want to introduce new states. So even like in this QED example, right? I just added by hand some charge Q things, but now you could ask which ones would you like to add? Do you want to add, 500 charge 1 states? Do you want to add charge 2 and 3? What do you want to add to kind of get rid of these higher form symmetries? Now, the other possibility is gauging it. Now, it turns out that this is actually a fairly subtle thing. Of course, you say, I know how to gauge a symmetry. I learned how to do that very early on. When you start talking about these finite symmetries like this, it turns out that, okay, there is a process. This summation over kind of the gauge redundancies corresponds to just inserting like a network of different kinds of operators. It turns out that when you do this, kind of another global symmetry kind of pops out usually. So it actually becomes very difficult to get rid of all the global symmetries through these kind of gauging operations. So I'm actually not going to do too much of that. I'm happy to talk through more like why that happens in detail, but it just turns out that it's very annoying that you cannot get rid of annoying. It's interesting that you cannot completely get rid of global symmetries by doing these kinds of gauging operations in these settings. Okay, so that's as far as bottom-up goes. I'm now going to kind of switch gears and start talking about kind of UV-motivated approaches, things where I'm going to use things I know about kind of short-distance physics to inform both how to build the quantum field theories I'm interested in, and then to study what happens to these symmetries in different kinds of systems. Okay, so as I mentioned, here are the ingredients I'm going to use. There are, of course, others, but these are just the ones I happen to like. So it's going to involve these closed strings associated with gravity, open string endpoints, the endpoints or the boundary conditions fluctuating, extra dimensions in various guises, and then kind of generalizations of different kinds of duality. So different ways of characterizing the same kind of quantum gravity background. And then holography, where we kind of characterize a gravitational system in terms of a non-gravitational system. Okay, so here are some different ways. I'm going to tell you about kind of a subject that's now rather old and mature, but what I'm going to tell you about is not old and mature, kind of a new twist on it, where we start from the extra dimensional world of string theory and start in manufacturing or engineering interesting quantum field theories, and then study their properties, both without gravity as well as with gravity. I'm also going to tell you about how to use holography. And basically, to kind of set the whole story up, we're going to start with a global symmetry in this kind of quantum field theory, a particular kind of quantum field theory known as a conformal field theory, a CFT. And then we're going to ask what happens to it when we pull it into the bulk. Something a little bit more abstract and mathematical, so-called cobordisms. I'll explain what this has to do with global symmetries at all. But we're going to see that actually, remarkably enough, having cobordisms around tells us about things having to do with global symmetries and their absence in gravitational backgrounds. And then lastly, one can go all the way back to things involving strings and how they embed inside of an ambient target space and ask what happens to the symmetries there. Now, this is too much to probably cover in one talk. So what I'm going to do is I won't talk about one, but I will try to kind of just give a sketch of how things work for the other three. Okay, so what do we do in string compactification? The idea is basically you start with this complicated world of strings, branes, geometry. It's very unwieldy and so on. But if you take various scaling limits and start stripping away all the complications of different kinds of quantum field of these gravitational backgrounds, you're often left with a simpler, it's still quite complicated, but a simpler quantum field theory that you can try to study in isolation. Okay, so here is a canonical picture that shows up a lot. We start with the kind of 10-dimensional world of string theory, and we have some 4D space, and then some 6 extra dimensions. And the whole point is that the field theory is kind of geometrically localized in some small, tiny patch of the full 6 dimensions. Okay, so what's going on? Remember I told you I had these different kinds of strings, these open strings that can kind of have these little hooks or ends to them, and as well as closed strings that can kind of just wander around. These are the ones responsible for gravity. In particular, these are the ones that control gravity in the 4D spacetime. So what I'm going to be doing is switching off the 4D Newton's constant. How am I going to do that? Well, this is basically like a big finite box for the graviton to explore. And if we make the box bigger and bigger, it will start escaping. So in particular, the four-dimensional Newton's constant is controlled by the inverse of the volume here. So as we send it off to infinity, it just becomes easier for the string to wander off. And then we're just left with this field theory sector by itself. Okay, so you can do this and actually start producing interesting new kinds of theories that are very hard to spot. So for example, so-called 6D interacting theories, the more technical name is 6D superconformal field theories. Instead of having 6 extra dimensions, you have 4. You can use this to make basically conformal fixed points in 6 space-time dimensions. And remarkably, you can actually classify all internal geometries relevant for those particular types of that class of quantum field theories. Just as a kind of, you might say, well, why don't you keep going with this research program? Well, it actually starts becoming increasingly complicated, even if you go down and just start talking about 5 extra dimensions. Even here, the classification is not completely known. But the point I want to stress is that you can use this to start building interesting field theories you may not have known about before. And you can, of course, start from some higher dimensional theory and then play the compactification game to quantum field theory to start making interesting 5-dimensional, 4-dimensional, 3-dimensional, and 2-dimensional systems. Usually these are coupling, and then the geometry of the extra dimensions plays a role in controlling or telling you what's happening in these lower energy systems. Yes, please.
A very naive question. So you're still building these wonderful theories. And then what you do with them?
Right. So this is one of the things you can do with them. So first of all, I think they're just interesting in their own right. But the other thing you can do with them is then you can start with one of these 6D theories, and you can start producing huge numbers of 4-dimensional strongly interacting theories, and then using the geometry of the extra dimensions. So for example, so let's say we had some 2-dimensional Riemann surface like this, for example. Then one of the things you can do is you can say, okay, if I fix this Riemann surface, I get a particular 4-dimensional field theory. A natural question to ask is, what happens if I start deforming the shape of this Riemann surface in some way? Well, I'm somehow changing from one field theory to another, but are they related? So this is a way of us to extract interesting lessons about what's happening in the 4-dimensional field theory. And you don't have to stop here. You can, of course, do a similar thing. So this is a way of generating interesting examples of dualities and constraining the strong coupling phenomena that's happening in the 4D field theory. That's one application to kind of lower dimensional systems. You don't have to stop at Riemann surfaces. You can do it with, you can do the split like this, or you have some 3-manifold or something like this. And then if you change the geometry of the 3-manifold around, you'll be making statements about 3D dualities. When you go to 2 dimensions and below, the process becomes a bit more subtle, but you can still kind of extract interesting things by saying, well, if I gave you an interesting 4-manifold like this, then you learn things about 2-dimensional dualities. And so you get kind of souped up versions of quantum field theories you already knew about from 2 dimensions, but now they kind of get connected by changing around and deforming these 4-manifolds. So these are some of the applications that have been kind of worked out. So for example, once you see the symmetries and selection rules for what's happening in, say, the abstract world is 6-dimensional field theory, those descend down or get inherited down into the lower dimensional systems. So that's one application. It's not the only application, but it's one broad class of applications. Yeah, please.
So does this 6D theory have a Lagrangian?
No.
So this is related to like little string theory, the 2-0 theory?
Yes. So 2-0. Okay. So 2-0 theory is a particular class of these SCFTs. The ones I'm doing, or the ones I was telling you about, have kind of the minimal supersymmetry 1,0. And
These are new.
yeah, most of these are new. And kind of the remarkable thing is that they all kind of look kind of like this, like a, I don't know, like a saturated fat molecule, if you like. They have like a long chain, and so a lot of these are new. So that's stuff I worked on a few years ago. But yeah, the point is that now with recent stuff we can now start calculating what are the symmetries, what are the selection rules. They don't have a Lagrangian, so good luck calculating anything, right? So that's part of the reason to kind of look for these other calculational tools. Yeah. And then little string theories is like an even further generalization where it's not a conformal field theory. It has now a bit of non-locality into the mix. But actually, they're not too far away from these. So morally speaking, they're in the same kind of universe of things. Yeah. Yeah, thanks. Okay, so how are we going to talk about symmetries in this setup? First of all, you build the field theory. Second of all, you start looking for the analog of these heavy lines like that we had. And then you look for how to talk about the symmetry operators that are acting upon the lines or whatever the defects are going to be. So here's the geometric setup. This part over here is the space-time. Here are the extra dimensions. Here's the heavy defect. What does it correspond to in the stringy setup? It's just some heavy object, like a brain, like the boundary conditions for the open string, that extends both in the space-time directions as well as in the extra dimensional directions. What is the symmetry operator? It's something that topologically links with this thing, both in the space-time as well as in the extra dimensions. And then this topological linking guarantees that it acts appropriately when it shrinks down or you try to cross it through. And it turns out that we actually know quite a bit about the world volume theory on these blue objects. And you can start with a topological field theory, Semino terms if you like, of this brain. And you can use that to actually extract what the topological field theory is that lives on this. So you get kind of like the leading order answer, which is this conserved charge. But then there's a bunch of subleading bits that are controlled completely by knowing what the brain world volume action is. Okay, so this has been done in a lot. I'm not going to go through all of these. There are applications of what you can do with these, both in 6 dimensions, 4 dimensions, 2, 0 that Tony was already talking about, metastable monopoles that kind of, and what happens to their magnetic one-form symmetries, even non-supersymmetric field theories. You can start studying topological features of this using basically this kind of setup. Now, the main focus I want to talk about, so this is just to say, we know how to make a bunch of examples and compute in a lot of these examples. But the question or the puzzle I wanted to pose was, what happened to those wonderful global symmetries when we switched on gravity? Okay, well, we start with the case with Newton's constant switched off, and then geometrically all you're doing is putting in like a capping type geometry to close it off, make Newton's constant finite. It might look like this, or it might even look wilder and more complicated. This is what actually happens in many string compactifications. You don't just get the single quantum field theory, you maybe get many, many quantum field theories together. Okay, so what happens when Newton's constant is switched on? Many things can happen to this defect. It might persist, it might be metastable, or it might be shared across multiple field theory sectors. Here's a picture illustrating. The key point is that now that everything is in a finite box, there's no sense in which the dynamical fluctuations can be switched off or tuned to 0. So what happens instead? Now all of these objects become fluctuating objects, fluctuating brains. So now it's dynamical in some way. So this is the key point. It's no longer like a purely topological thing. It starts coming to life in its own right. So it's picking up a mass or a tension, or it starts fluctuating in some way. It's no longer completely decoupled from gravity. It can also happen that the thing just doesn't persist in the bulk. So what happens instead is it kind of lives for a bit of time. Then there's some decay rate controlled by the fact that Newton's constant is now non-zero. So it's not, so in other words, the Planck scale has been brought down from infinity to some finite value. So there's some decay rate control now by Planck scale effects. And lastly, it could be that you have multiple field theories, and then a line operator defined in one theory is actually shared between multiple sectors. So these may be seemingly completely decoupled, like there's no like light states that connect the two, but there can nevertheless be subtle topological correlations between different field theories once gravity is invoked, or once gravity is switched on. Okay, so what happened to all the symmetry operators? They became dynamical brains. That's the main point. So all of these topological things start coming to life as new kinds of objects. And the thing I want to stress here is that all of these examples are kind of known brains that we already kind of knew about. And what we're doing is we're just asking, we took some limit to kind of freeze out the dynamics. And then once we switch on gravity, they start coming back to life and fluctuating. That seems to be the main lesson from all of these string compactification examples. But you might say, well, surely not everything is coming from the brains you already knew about in string theory. Otherwise, what are you doing? You're just rehashing old things. Well, so what we're going to do now is actually flip the game around and ask, if I gave you my favorite topological symmetry operator, could I predict for you new kinds of brains? Yes, please.
So I got a little confused. So very naively, I would have guessed that if you have some field theory with some interesting line or surface operators, you thought you could count. What would happen if you include gravity effects is that you have also various kinds of endpoints you could put on them that are very heavy, but are there in the theory of gravity. Those would be the brains, the extra brains. That you have a completeness of spectrum kind of idea.
Yeah.
And that naively isn't a statement about the symmetry operators becoming topological. It's just that they.
Yeah, so that's we'll see that happening also. So that also happens. So that also happens for sure. And I might run out of time, but that for sure also happens for sure. And I'll tell you about what you can do from that point of view as well. So the only thing I'm doing here is just saying like, here's some specific examples where I can definitely track what's happening. Yeah. Yes.
How is this example telling me what happened to the baryon number when you put it in the black? So I have double symmetry, which is baryon number, and we say, okay, that symmetry doesn't exist anymore in the presence of gravity. And the example is I put the baryon
Right.
in the black hole, and now I don't have any way of measuring it. So how is this picture helping me understand what happened?
It's not helping you to understand that part of it. So that would be more, it's more related to what Alexei was asking about, where he's saying, well, I get some extra pair creations and so on like that. There's kind of new things that are coming. So one way of saying it is, look, the baryon number was just broken by some Planck scale effect, and that's at the end of it as a global symmetry.
So it's not still there somewhere in the theory.
It could be gauged or it could be broken. So one answer is just going to introduce some new stuff. It's broken.
Okay.
The other answer is, no, I really want this to be an exact symmetry. I'm going to gauge it, okay? Then the statement is that, okay, well, now it's a gauge symmetry, so there's some kind of trailing like Wilson line that attaches, like the gauge, some line that attaches to the baryon that you're talking about. So when you try to pull it through, you're still seeing the Wilson line or this thing trailing out behind it. So we thought about like exactly this kind of thought experiment, like why can't I just now take these linkings, throw them into black holes, and ask what happens? This turns out to be a lot more subtle, in part because let's say we talk about a black hole like this. There's many so let's say I want to talk about my favorite charge thing, and I want to watch what happens as I throw it in. So I'm gonna draw my little guy like this, and then I'm gonna draw the topological guy we've been talking about, right? The very strange thing about having it be topological is that, well, I just told you it didn't depend on the metric. So why don't I have the operator go like this? Or maybe I let it extend behind the horizon and then come back out. It gets very confusing quickly about what exactly you mean. Now, the statement about giving it a mass means that, no, you can't just let it dip in and out of the horizon. Now that it's got a mass, it's going to feel these effects more. But so in other words, it's not like a pure topological object anymore. So that gets towards the question you're asking, but it's motivating still, like a lot of what we're asking about. Yeah. So yeah.
For that question, I mean,
Yes.
Isn't it clear that when you throw charge into a black hole, global charge, you have no flux outside, so you can't tell how much charge goes into the black hole. You can't measure the flux,
Unless it's gauged.
right? Unless it's gauged.
Unless it's gauged, yeah.
But I'm just saying, but that's the argument, right?
That's the argument. But now do it
If you
again.
just throw global charge,
Absolutely.
no flux at infinity, you can't tell how much charge went into the black hole because you can't measure it.
Well, but what if you let the black hole radiate?
But if you have but then if black hole's charged and you can measure how much, then you can measure from the flux lines, you can measure how much charge went in, you can keep track of it.
Yeah, now do it again for all of these weirder global symmetries. So what you just described is like why nobody thinks there's any global symmetries.
Yeah.
But now do it again for these more abstract, crazy ones where it's not as easy to kind of say, oh, I'm measuring it. That's where it's not so easy to kind of nail it down. But yeah, absolutely,
But for baryon number, you're saying the symmetry that I started with for baryon number isn't just sort of lost and redefined in terms of this kind of picture. It's just broken.
Yeah, just straight up broken. Yeah.
No, but I think you have to make reservation because we live in a localized world, right? We believe that if you do experiment right in this room, you measure what happens in this room, not in a very, very, very distant black hole, right?
Yeah,
So,
but it could be that it's just an approximate symmetry at low energies. That baryon number is actually really just broken at the Planck scale. And so we don't have an experiment that we can do that actually sees, I mean, even grand unified theories will break.
it is
baryon number,
broken,
right?
and even in the standard model, due to Hopf instanton, it is broken, but with probability which beyond lifetimes of universe. If something happens beyond this span of lifetime, okay, in practice, it's
Yeah,
Okay, okay. I'll try to go fast through these last few slides. So holography is this very nice correspondence between talking about a gravitational spacetime with negative cosmological constant, kind of the opposite of where we might be living in like a de Sitter phase where it's looking like it has at least approximately a positive cosmological constant, and then describing that in terms of some quantum field theory that doesn't even have gravity. So one of the really nice things here is that one of the classic things that was kind of early established is that global symmetries of this boundary system correspond to kind of gauge symmetries of the bulk. Of course, what I'm going to ask is, now what happens if I give you these fancier notions of global symmetries? What happens to them in the bulk? And the other kind of intuition here is that somehow smearing operators out or allowing a bit more local corresponds to dipping further and further into the kind of what we call the radial direction of ADS. So you can think about it as like some filled cylinder. And as you go further out, you're going closer to the boundary of the cylinder. As you go further into the interior, you're going to like deeper into the infrared of the field theory and so on. Okay, so let's start with our symmetry operator here in the boundary theory. It's linking with some charged object. As you pull it into the bulk, there's a bottom-up argument you can give that actually, again, turns into a dynamical brane. So precisely the same kind of thing we saw happening from the string compactification point of view, but now nothing to do with a particular string compactification, now just using things we know about holography. And indeed, the first examples that were worked out were kind of doing it from the string compactification background point of view. You start with a known brane and you turn it into a symmetry operator. So this pushing, kind of running this whole picture in reverse. You start with a dynamic brane and you push it into the boundary, and then it turns into a topological thing. Essentially, the dynamical parts of the brane start freezing out as you push it into the boundary. Can you do the converse? You can. And so in a series of papers, what we did is we started figuring out that if you have this linking here and you start smearing out the location of this thing, it's doing something interesting from the point of view of the bulk. It's starting to look like it's inducing some stress energy in the bulk system. I'm going a little bit fast so I can address some other questions that were asked later. The point is that it looks like the operator starts jumping as a function of this linking and smearing. So there's actually a one-to-one correspondence between starting from a symmetry operator in the boundary system and then turning it into a dynamical brane in the bulk. So in other words, there is no topological operator that lives in the bulk. In particular, you can start with a candidate global symmetry operator in the bulk here, push it to the boundary, and then pop back out. I just told you that if you start with a topological one, it turns into a non-topological thing. It starts getting fluctuating dynamics when you pull it back out into the bulk. So there's a contradiction if you try to say, oh, it was actually topological. You push it and you pull it back out. And it turns out that you cannot maintain these two kind of contradictory points of view. There are, of course, some subtleties to this I'm glossing over, but this is the main kind of thrust of the argument, that the global symmetry is not showing up. Now, again, the surprising thing here is that it's not using black hole arguments in any way. Those seem to be much more challenging to kind of completely leverage to make these statements sharper. This is more in the kind of better established world of ADS CFT, where we think we have more control over what's happening quantum mechanically in the gravitational system. So symmetries lead to branes. Sometimes they're known objects, things we already knew about from string theory and string compactifications. But sometimes we get new objects, ones that aren't protected by supersymmetry. They look wilder from the point of view of geometry. I'll tell you more about this one in just a moment. But the point is that any symmetry you can think of in the boundary CFT is then a prediction for a brane in the bulk gravitational system. And one of the things we've been doing is exploring the properties of those kind of new objects, new kinds of branes that have been showing up. Okay, so now to connect back, a question that was already asked is, well, why don't you just add more states to the theory to break all the symmetries? This has to do with cobordism. So what is a cobordism? Got 5 minutes to tell you what a cobordism is. Okay, great. It's a way to think about equivalence relations between different kinds of manifolds. So the K here refers to the dimension of the manifold. So K equals 1 would be like a circle. K equals 2 would be like a 2-sphere or a 2-torus, something like that, and so on. So the idea is that when you look for two manifolds, X prime and X, and if they share, or if there's a bulk object which has boundaries given by this, we say that X prime and X are cobordant. So they're basically going to be identified. If you want to kind of simple example, take a donut. It has a 2 torus as well, roughly as a 2 torus as its outer surface and it's solid in the middle. Scoop out a donut hole. There is a surface given by a 2-sphere here, and then this is Borden, therefore, to the 2 torus. Okay, so this is a simple example illustrating this is a very coarse topological notion. It's more coarse than even like talking about the genus of a Riemann surface, because this is genus 0, this is genus 1. You're clearly deforming one into the other.
Is it a hole which goes through?
No, you scoop out a ball inside of it. So imagine like the baker made a mistake and they didn't like make it completely solid.
ball.
So your T2
No,
is
not a bite. That's this is
It's an air bubble inside, yeah. Yeah.
T2 is a solid
like a
T2.
bubble.
No, the T2 is just the surface. So in this example, the solid donut is the 3 manifold. And this is the thing that's boundaried. So here,
It's an air bubble inside.
yeah,
Embedded bubble inside the.
Right, imagine just a bubble,
yeah, like just a bubble.
spherical bubble inside the torus.
I
Yeah.
see.
Yeah, so the baker just made a mistake, or they cheated you. Okay,
The bubble's not part of this torus. Right? The torus is the surface, right?
that's right. That's the surface. That's the outer boundary of the donut. And then the 3 manifold, the thing that kind of connects the two, is the solid part of the torus.
You see, so your donut hole is a separate.
Yeah. That was me just trying to say like you scooped it out and then you sewed it back together or whatever. And so donut, but yeah, that's the idea.
So
That's
it's
going into the
it's a
surface.
donut, let's say, with spherical empty space.
Inside of it, yes, exactly.
And then you combine the 2 surfaces of the sphere inside.
Correct.
The torical surface
You got it.
outside.
Yes.
And what happens?
No, so then the point is that these are in the same equivalence class. So this is to show you that it's a very coarse notion of equivalence class of manifolds. So many different manifolds will be identified as being cobordant to one another. But you can make it more complicated by saying, well, maybe there's some interesting, bundle or something like this. There's, non-trivial gauge field on the outside or the inside. And so then maybe I can't deform them into each other. So maybe there's an interesting, charge I want to talk about in infinity. Then I can't deform them into each other. Okay, what happened? Okay, so the point is that if you have one of these non-trivial Bordism classes, secretly you're talking about it having a conserved charge. What does this look like to an observer? Remember we had this picture of shrinking operators and topological operators. You can glue this tube thing that I was telling you about earlier to somebody who's looking at this very far away. It looks like a defect which fills the p-dimensional space and then just fills a little dot in the extra dimensions. This is precisely the definition of having a p-dimensional defect, and the charge it's carrying is that cobordism class. Okay, next, exciting. Remember what we said. We had this breaking this p-form symmetry, right? We wanted to add a new state in here, like this, and then we say we're going to break the symmetry by destroying the topological linking, by adding this new state in. Well, this is precisely, or this is one way to think about a recent conjecture that was made about getting rid of cobordism groups. Sorry, that cobordism groups are trivial. The idea is that this new state is simply a new object in the quantum gravitational system. The only thing we're using here is the topology of these cobordisms to then tell us about new states and objects. Okay? So every time that you calculate a non-zero value of the cobordism group, you're actually predicting a new object in the quantum gravitational system. So again, this is nothing to do with supersymmetry or anything like this. It's predicting the existence of the object based on very coarse topological notions. So remember, a 2-sphere and a T2 are being identified. So it's going to miss things for sure, but it's at least a very robust topological condition to see something like this show up. Okay, so people have used this. So in the original paper that McNamara and Baffa wrote, they used this to kind of post-dict some things that were already known about in string theory. But then you can start predicting things. You can also do very non-trivial checks in supersymmetric backgrounds and ones that involve dualities. It's something that we've been doing for a few years now. And it also leads to kind of non-trivial predictions for new kinds of things. I'll focus on this one over here. I realize I'm basically out of time, so maybe I'll speed through it. But the point is that it's a new kind of non-supersymmetric object. Okay, here's some examples of the calculated. So just to let you know that it's pretty non-trivial to get them all. And then the kind of brain interpretation. Some of these have already known brain interpretations, but then some of them are completely new. Okay, so essentially, you can start building these things. Turns out to be non-supersymmetric. There's one that was already kind of known from this, and then there's a new one that looks again like an 8-dimensional quantum field theory. It looks like it's probably interacting, but it's still, the picture is still a bit murky and we're thinking about it. But the point is that, you can start analyzing properties of this predicted new object. So for example, we wrote down a class of space-time metrics that describe them. Here's an example of what it looked like in detail. It has some free parameters because this is just a low energy approximation. We don't know all the microscopic details to pin down all these numbers, but it's at least something that we can kind of now sharply point to is coming out from these kinds of things. Okay, I'm a little bit over, so let me wrap. So what was this talk about? It was telling you about field theory, gravity, and symmetries and how they all interplay with one another. So what's the short term? I kind of view the interesting thing here is using symmetries to find a lot of structures, both in the context of field theory and gravity. I told you about some examples. The one I'm actually most excited about is this R7 brane, and in particular, like, in what sense is it a genuine 8-dimensional quantum field theory? This would be like a non-supersymmetric version of the thing Tony was already saying about like the 6D 2,0 theory, which is already kind of very complicated. That one has a lot of supersymmetry. This one has no supersymmetry. Having this thing pinned down as like a genuine field theory would be, I think, very, very exciting. It seems to exist, but what the properties of it are still kind of mysterious. That's in the short term. Medium term, I think, one of the things that was showing up quite a bit is different kinds of geometric structures, still perturbative type things, and to some extent still supersymmetry. I think kind of relaxing each of these, making them, deforming away from each of these is a very interesting kind of medium term thing. And then long term, I think a very natural question is, where did all this like macroscopic, interesting topological structure come from in the first place? So a picture that I've kind of been motivated by for many years now is to kind of try to think more about how these kinds of things show up. Starting from, say, whatever this picture is in terms of some pixelated geometry, and then how our smooth macroscopic space-time emerges from it. Okay, I'll stop there, and thanks very much.
Questions, please.
When I think of quantum gravity, I'm thinking that I want to be able to calculate, say, some process, but at energies much higher than the standard theory would go.
Right.
So to include, say, the gravitational interaction. And, part of the way there is maybe through supergravity, but that's still an effective theory. They still have everything is 1/m Planck squared, things like that. So
right.
Are these all just attempts of sort of poking around to try and find which is the correct description of how I do such a calculation, where I want to do a calculation at high energies higher than the Planck scale?
Well, that's part of it, but it's also to, okay, so why would you want to do such a scattering experiment? So one reason to do it is to say, I want to look for like, interesting kinds of resonances, new kinds of objects, right? So what do you look for? Bumps or, interesting poles in the, in the S matrix, something like that. So, okay, you're looking for those kinds of objects to show up if you do your scattering experiment at sufficiently high energies. From that point of view, this is trying to inform what are the places where you expect new kinds of poles and so on to start showing up. So that's how I think it ties into that part of it. But there's a general question I think about if somebody just hands you a quantum field theory, is it always possible to kind of couple it consistently to gravity? How do I know which ones are the right quantum field theories? How do I know which ones are the wrong ones? So
are you referring to different vacua or a different, so if I'm given, so I have the standard model and I know I have to go beyond the standard model.
right.
And so
Yeah, what should we add beyond the standard model? So am I allowed to add whatever I please in terms of, some extra, quantum field theory sector or the non-trivial constraints on that sort of thing? So am I allowed to add whatever states I like? Can I add them in whatever representations I want? These kinds of things are hard to kind of nail down from a purely bottom-up point of view. And that's part of the reason to kind of try to merge it with these other ways of thinking about it. Yeah.
So just coming back to this eight-dimensional.
Yeah, sorry I rushed it. Yeah.
Was it secretively supersymmetric, and when you added these objects, you just broke supersymmetry? Or is it genuine? I mean, does it start out life supersymmetric somewhere, and you broke supersymmetry, and that's why it's not supersymmetric at low energies? Or
so the way we so it really is. It appears to be so people have known about non-supersymmetric objects in string theory for a long time. The problem with most of them is they're unstable and they basically die right away. These ones,
Right, there's also,
yeah, so you can write down non-BPSD branes and all of these, but they have like a very short like string scale lifetime. So it just usually tells that you expanded around the wrong vacuum and you're going to roll down to some other minimum. These are a bit different because they're kind of topologically protected by this cobordism group thing. The other ones are not. So the point is that this thing is carrying a conserved charge, and that makes it hard to get rid of it. And in particular, it's hard to get rid of it in the kind of gravitational effective field theory that you get. That's what makes it exciting. So now how did we know that this was breaking supersymmetry? Well, we computed that when we looked at like what happened to the killing spinners off at infinity. So this thing is in 8 dimensions. So it's there's some codimension 2 thing. So it just fills a point in say some 2-dimensional transverse thing. And what we did is we looked at the behavior of the spinners off at infinity, the candidate supercharges off at infinity. You could kind of guess that it was going to break supersymmetry because it's doing something very non-holomorphic to some of the effective fields. So usually in nice supersymmetric situations, there's a nice holomorphic structure showing up. That's completely destroyed by having this particular, this turns out to be a very nice way to package the fields into a nice supersymmetric object. Or that's completely messed up by this kind of thing, where it basically just does a parity type reflection on the kind of axionic degree of freedom of this particular effective field theory. So those are the indications that it's not breaking, that it's not preserving supersymmetry. And then, yeah.
If I may very quickly, so I already asked this question. So you have this dimensional reduction, and
Yes.
you've got in your theory progressively lower dimensions.
Yes.
So is there a way to say something about this theory? Is there a way? Do we know what to expect about them, relation functions, or does this construction allow you to
yeah. So for example, one very robust thing you can do is use the anomalies and things about that. So those are particular kinds of current correlation functions or divergences of currents, and then how those things show up. You can start with the known anomalies in say the higher dimensional system, and then start dimensionally reducing to then extract what the anomalies for these strongly coupled lower dimensional systems are. That's one thing for sure you can do. And for example, you can count, morally speaking, the degrees of freedom. So these things like these stress tensor correlation functions would count effectively the number of degrees of freedom. It's again controlled by what's happening up in the higher dimensional theory. So all of those things can be counted in some way. Yes, please.
Is there apparently the same? Is there any hope that this will be measured? That this will be real stuff that can be seen in an experiment?
I mean, I'm always hopeful that will happen. But yeah, I think actually, so if you'd asked me, like even the 6-dimensional one, you might have said, oh, come on, this is a total fantasy. But actually, nowadays, people can kind of synthesize very interesting, like, 2-dimensional materials on quantum chips where it's a high genus Riemann surface and so on. So I've asked some of my friends who know more about this, and the point is that a priori, there's nothing to stop you from doing this in any crazy number of dimensions. So from that point of view, there might be a way to kind of get more direct access to that sort of thing. And we're thinking about that. We haven't, I mean, I can tell you more about that if you want, but one of the things we're looking at is, for example, is there like a generalization of, like Chern insulators and, these kinds of like topological band structures that show up straight for like 6-dimensional systems where, you don't necessarily have, as clean a control over, say, the many-body physics. But nevertheless, we have enough topological control to say interesting things. So for example, we don't have the analog of, if you like, the microscopic picture in terms of like, free Dirac fermion or Dirac fermions or many of these things moving around, like in the case of 2+1 or 2D systems. But what we do have still is the generalization of, say, fractional quantum Hall. So we do know what that looks like in these 6- and 7-dimensional systems. So that sort of thing provides a point of entry to kind of look at those things. And then if they can be synthesized, I think I would say that's in between like pure nature and then having an experimentalist do something crazy that, looks very contrived, but nevertheless is, getting towards that. Yeah.